Okay, so we're going to continue on with our discussion of chapter 4, which is conformational analysis. Previously, we were looking at dash wedge notation and conformational analysis for cyclohexane systems. Remember, a wedge indicates that our substituent is pointing up. So if we were to draw out our chair conformation for this molecule, if we label this as carbon number 1, then in this case, our axial substituent is pointing up. So this thiol would be in the axial position, pointing up at carbon number 1, while our hydrogen would be equatorial, pointing down. After a ring flip, as we discussed from our student solutions, we would end up with carbon 1 being brought down, carbon number 4 being brought up, and in turn, our thiol would be pointing up still, but it would be in the equatorial position. Let me redraw this to make this a little bit neater. In this case, the thiol is now equatorial, but it's still pointing up. After a ring flip, your stereochemistry remains unchanged. Does this make sense to everyone? This is review from the example that we covered in our previous session. So let's keep going now, and let's look at cyclohexanes with 2 or more substituents. So a cis cyclohexane ring system has our substituents on the same face of the ring, either both up or both down. So for example, we have a bromine with a wedge pointing up and a chlorine with a wedge also pointing up. Now, just because both of our substituents are pointing up does not mean that both of our substituents are necessarily axial or equatorial. So let's make a model. Let's make a model of this structure. So after putting together a model for this structure, here's what we get. So as we can see in our model, we've arbitrarily chosen to place chlorine on carbon 1 and bromine on carbon number 6. It's completely arbitrary. You can draw multiple chair conformations for the same compound, just depending on how you number your carbons. So continuing on from that framework, we see that our chlorine substituent is axial and pointing up. And looking at our bromine substituent, is our bromine substituent axial or equatorial? It's equatorial, yep, but it's still pointing up. Okay, of course there are many ways to draw this structure. If you wanted to take an alternative view, if you label your carbons differently, your chair conformation that you've drawn will look slightly different. So now, subjecting this molecule to a ring flip, I'm going to bring carbon number 1 down and carbon number 4 up. And after a ring flip, we end up with the following structure. Okay, now analyzing this structure, as we can see, our chlorine is now in what position after a ring flip? Our chlorine is now in what position? It's equatorial and it's pointing up, and our bromine is now axial, pointing up. Does everyone see our axial bromine here? Does everyone see the axial bromine? Perfect. So again, after a ring flip, you need to respect both the relative position of our substituents and the stereochemistry of our substituents. So let's look at another example. This time we're looking at the trans isomer. So in this case, we have our bromine pointing up with our chlorine pointing down. In the trans cyclohexane isomer, the substituents are on opposite faces of the ring. Okay, so let's look at the chair conformation for that. If we label chlorine arbitrarily at carbon number 1 and bromine at carbon number 5, we would get the following structure. We would get the following structure. And as we notice in this structure, if we pay attention to our chlorine, is our chlorine axial or equatorial? If it's pointing down, is it axial or equatorial? It's equatorial, yep. So this chlorine is equatorial, pointing down. Additionally, looking at our bromine, so looking at our bromine atom, is our bromine axial or equatorial? Is our bromine axial or equatorial? It's also equatorial, but this bromine is equatorial, pointing up. So after a ring flip, when we bring carbon 1 down and carbon 4 up, we exchange our axial and equatorial positions. So we move carbon 1 down and carbon 4 up. And as we can see now, our chlorine is now in the axial position and it's pointing down. While our bromine is now in the axial position, pointing up. Does everyone see how our bromine and chlorine are on opposite faces? Does everyone see how bromine and chlorine are on opposite faces and are trans to each other? Perfect. So those are the cis and trans isomers. You should be familiar and comfortable drawing cis and trans isomers for cyclohexane systems. Yes, ring flips will always be with carbon 1 and carbon 4. So when drawing a chair conformation from dash wedge notation, you need to make sure the 3D orientation of each substituent must be considered. So depending on the positions of our substituents and whether they're cis or trans, we have a different axial and equatorial relationship. This table, you're not meant to memorize it, but it's a useful tool for checking your work. So for example, this structure here is a trans 1,2 disubstituted cyclohexane. And as we'd expect, so for a 1,2 trans disubstituted, we have either an axial and axial relationship or an equatorial relationship. So this table serves as a way of checking your work. If you want to work on some of the homework problems or other related chair conformation problems, and you want to make sure you're on the right track in terms of assigning your substituents as axial or equatorial. Does that make sense to everyone? Okay, let's keep going now. Now, there are tricks to quickly draw cyclohexane conformations. So the trick starting out is you identify a substituent with a wedge stereochemistry pointing up, and you label that carbon with an axial label. You'll put this first wedge carbon at carbon number 1. Okay? So that's why I've drawn out my axial bromine at carbon number 1. Now, counting clockwise around the ring, you're going to label the adjacent carbon with an equatorial label. If that carbon has a wedge up, the substituent will be equatorial in the first chair conformation. So notice we went axial, equatorial, and both of these substituents are pointing up. You'll keep counting along the ring. So we go axial, equatorial, counting clockwise around the ring. So at carbon 1, we have an axial substituent if it has a wedge. Carbon 2, since it also has a wedge, will be an equatorial substituent. Carbon 4, since it also has a wedge, will be equatorial pointing up. As we notice, if we look at this chair conformation, do we see how all of our substituents with a wedge are pointing up? Does everyone see that? How all the substituents with a wedge are pointing up? Okay, so that's one way of checking your work. So this is a shortcut for drawing out chair conformations. You label alternating axial, equatorial. If it has a wedge, it follows this pattern. So all substituents with a wedge will follow this pattern at each of the indicated carbons. And this allows you to very quickly place your substituents with the correct stereochemistry and in the correct axial or equatorial position. You're welcome to use this shortcut or not. It's not necessary to solve these problems, but it's useful to save time. Does that make sense?
What's the ME for? Does it just mean me?
What's the, oh, ME is the shorthand abbreviation for a CH3 group. ME or methyl is an abbreviation for CH3. Does that make sense? Perfect. So let's suppose you have alternating dash and wedge stereochemistries. So to quickly draw cyclohexane conformations, in this trick, you identify a substituent with a wedge stereochemistry and you label that carbon with an axial label. So this bromine is axial pointing up. Now we continue on with our axial and equatorial numbering. So axial, equatorial, axial, equatorial, axial, equatorial. This would be if all of our substituents had a wedge. However, because our substituent has a dash, we instead use the opposite label. So if the carbon has a dash, the substituent will be axial rather than equatorial in our first chair conformation. So then, from this, if our first bromine is axial pointing up, rather than having our chlorine in the equatorial position, our chlorine is instead in the axial position, this time pointing down. Does everyone see the change that happens when we have a dash substituent? Does everyone see the change that occurs when we have a dash substituent? Okay. So you'll keep counting around the ring, and if it has a wedge, you use the set of labels in red. If it has a dash, you use the opposite set of labels in blue. So the key distinction, because the chlorine has a wedge, because the chlorine has a dash, it's pointing down. So instead of an equatorial chlorine, we have an axial chlorine pointing down. While both of our wedge substituents are, in this case, our bromine is axial pointing up, and our methyl is equatorial pointing up. As we can see, all of our substituents with a wedge are pointing up, while all of our substituents with a dash are pointing down. Does that make sense? Okay. So this is a nice little summary of converting dash wedge structures into chair conformations. So all the hydrogens labeled in red will get a wedge. So we have alternating axial and equatorial wedge hydrogens. And for our dashed hydrogens, we have alternating equatorial and axial hydrogens. Does everyone see this alternating pattern for our dashed and wedge substituents? You don't need to be too familiar with this shortcut, but I just find that it saves time if you know where to place your dash and wedge substituents. Does this shortcut make sense to everyone? Okay. So let's apply what we've learned and let's try to draw both chair conformations for the following structure. So let's take about 2 to 3 minutes and let's try to draw out the chair conformations for the following structure. So I'd like 2 students or more to draw out the chair conformations for the following molecule, making sure to respect the stereochemistry for this trans 1,3-disubstituted cyclohexane. So let's try to have a few students use the annotate tool and try to write out the 2 chair conformations for the following molecule. So let's keep working on this example and let's have a few student volunteers write out their proposed chair conformations. and we'll discuss this example in about 2 to 3 minutes. And if you have any questions working through this example, don't be shy to ask it in the chat or verbally. Yeah, that would work. That's another way of drawing this chair conformation. But yes, that chair conformation as drawn would work perfectly fine. The ethyl group is pointing up. The methyl group is pointing down. Yep. Could you draw, would someone like to draw another chair conformation for this molecule? Would someone like to draw the ring flipped chair conformation for this molecule? Would someone like to propose the ring flipped form for this molecule or draw the ring flipped form? Let's try to get another student contributing, or the same student contributing a second drawing, just so that way we have a complete solution that we can discuss. Would someone like to propose another chair conformation using the annotate tool? If not, we'll discuss in about another minute. I really want to make sure students are comfortable drawing both chair conformations, as you have to consider both chair conformations in order to assess reactivity and the most accessible and the most prevalent conformation at equilibrium. One thing to note is after a ring flip, the orientation of your cyclohexane ring changes. But that proposal is interesting to consider. Do you have a revision for that proposal? it's on the right track. The only thing you'd have to do is just make sure your cyclohexane ring is in the right orientation. Okay, so let's clear this and let's discuss just to highlight this idea for the ring flip. So first and foremost, using our shortcut, we know this ethyl group will be pointing up, this methyl group will be pointing down. I can use my shortcut numbering of axial, equatorial, axial. Because the substituent has a dash rather than a wedge, I use the opposite label. Then I write out my carbon numbers, number 1. So then I put my ethyl group at carbon number 1, and it's going to be axial. At carbon number 3, I'll put my methyl group. And in this case, it'll be equatorial, pointing down. Does this first example make sense? Does this make sense to everyone? How we read dash wedge notation, noted the ethyl will be up, the methyl will be down. Okay, now after a ring flip, and this is really important, our carbon 1 is brought down, carbon 4 is brought up. And in our ring flipped structure, the orientation of our cyclohexane ring has changed. We now have carbon number 4 pointing up and carbon number 1 pointing down. Let me redraw this so that way it's a little bit easier to see. Okay, now after a ring flip on carbon 1, my ethyl group is now equatorial. So in this case, this ethyl group is equatorial, still pointing up, and our methyl group, which is at carbon 3, is now axial, pointing down. Does this make sense to everyone? Does everyone notice how our cyclohexane conformation, how the orientation of our cyclohexane ring has changed when we undergo a ring flip? It's really important because if you do not correctly draw your cyclohexane chair conformation, what you're actually doing is you're drawing the enantiomer of your original compound, a mirror image of your original compound with a different stereochemistry. Does this example make sense to everyone? Does everyone see how the shortcut can potentially save you a little bit of time? Really, it depends on what you're more comfortable with. Okay, so let's keep going. And what I'm going to have you do is I'm going to showcase the first one and you'll do the next two. So we're asked to draw chair conformations for the following structure. So I find my carbon with a wedge, I label it carbon 1, and it'll be at the axial position. Carbon 2, it would be equatorial, but since it has a dash, it's assigned at the axial position. I draw my chair conformation, and I place my methyl group at carbon 1, and it's axial, pointing up. The ethyl group, it has a dash, so it's pointing down, and this ethyl group would be axial, pointing down. After a ring flip, carbon 1 is brought down, carbon 4 is brought up. So then at carbon 1, our methyl group Our methyl group is now equatorial, pointing up. And our ethyl group at the adjacent carbon is now equatorial, still pointing down. Does this make sense to everyone? Does this make sense to everyone so far? So, with that representative example done, I'd like you to take a moment and look at the following two molecules, and let's spend 6 minutes drawing out both chair conformations for the following two molecules. And don't be shy to use the annotate tool to share your proposed drawings, or you can message me with a picture of your drawing in the chat. Either would work. It's really important that you practice drawing out these chair conformations from dash wedge notation, because in this chapter and in later chapters, we're going to be analyzing these structures in detail. So let's work on this for about 5 or 6 minutes, and I'd like to see from the class at least 4 structures drawn, 2 for each of these two molecules. Because remember, we have 2 chair conformations. So let's keep working on this example, and we'll discuss in about 5 or 6 minutes, or until we have 4 responses. And just as a reminder, the annotate tool is accessible in the little tab titled Meeting Options under the Zoom chat features and under the Zoom view option features. And I would, if possible, if you could number your carbons, that would be very helpful for our discussion. So the structure drawn is not wrong. It's not wrong. It's perfectly fine. It took me a moment because you have your carbon 1 labeled at a different carbon than I traditionally start at, but there's nothing wrong with the structure that you've drawn. Would you be able to draw the ring flipped form? And while we're working on this one example, another student can also work on this top example. I really encourage you to use the annotate feature to share what you're thinking as you work through these problems, as that allows me to provide feedback. So we need about 3 more structures, the second chair conformation for this bottom structure and both chair conformations for the top. So let's keep working on this example and advancing our discussion. And let's try to get a few more annotations and we'll discuss in about 4 minutes. And is everyone comfortable using the annotate feature? If not, you can also share a photo of your proposed structure or share your screen and I could view the structure that you've drawn. And don't be shy just because a student is working on one of the problems that you can't propose your structure as well. As long as you're able to use the annotate tool or share your structure in the chat as a photo, I'd be happy to provide feedback. And don't be shy to contribute your structure. We still have 3 structures remaining to draw, and I'd really like to see some proposed student solutions using the annotate feature before we begin to discuss these examples. And we'll discuss in about 2 to 3 minutes. Let me just take a look. A student sent their image momentarily, so if it's blocked out, I'm just looking at what the student drew. Yep, that looks good. Thank you for sending your image file in the chat. Let's keep working through this example, and for students using the annotate feature, don't be shy to draw out your structures using the annotate feature. For the image I received in the chat, yes, they're all correct. Yep, it looks good. The only thing is you don't put the wedge when you're drawing the bond line structure. But other than that, it looks great. It's interesting actually when I see what the students are drawing. Everyone starts off with the opposite chair conformation. I'm not sure where that habit came from. It's perfectly fine. It just takes me a moment when I'm looking at it to figure out what's happening. And the proposed structure that we have in pink, it's not quite an ethyl. It would be a tert-butyl, but your relative stereochemistry looks good. I'd like to see a few students draw the ring flipped form just to make sure everyone knows how to do a ring flip for each of these chair conformations and showcase the ring flipped form. And I'm mainly looking that your carbon numbers are consistent and your stereochemistry is consistent. And so we have our ring flipped form, and that ring flipped form looks great. Would anyone like to showcase the ring flip form for our second structure? Or would anyone like to draw a few chair conformations for our second structure? If not, we'll discuss in about another minute. And thank you for the students who are sharing their contributions. I find the act of drawing and proposing a solution while you're working through a problem is invaluable to retaining the material. If possible, in that ring flipped conformation, the carbons are drawn in a way where it's a little hard to tell. I would just correct the skeleton and then add your substituents. And then, okay, perfect. And could you label the substituents now? Okay, so let's talk about this example, because there's one thing that I noticed is that your relative stereochemistry is correct for the chlorines, but your carbon numbers, when you undergo a ring flip, you need to make sure that your substituents are attached to the correct carbon in the final structure. So let's talk about both of these examples. The responses I've received look great. Everyone's on the right track with regards to these examples. And let's now discuss the instructor solution. So I'm going to label my counting method. So axial, equatorial, axial, equatorial, axial, equatorial. Because we have a dash instead of a wedge, I use the alternate label of axial. So I'm going to draw my first chair conformation, putting the methyl group at carbon 1, and I'm going to label my carbons. So now I'm going to draw my first chair conformation. My methyl group is axial, pointing up. The tert-butyl group is equatorial, pointing up. And then my other methyl group is axial, pointing down, because it has a dash, which indicates it's pointing into the page. Now I'm going to put my carbon labels. 1, 2, 3, 4. Carbon 4 goes up, carbon 1 goes down. And as a result, the orientation of my cyclohexane ring changes during a ring flip. So carbon 4 is here, carbon 1 is here. As a consequence, for carbon 6, my axial substituent is now equatorial. And at carbon 1, likewise, my axial methyl is now equatorial pointing up. So in this case, we have a methyl that's equatorial pointing up, while the methyl at carbon 6 is equatorial pointing down. Does everyone notice how I'm making sure that my carbon numbers are consistent? Does that make sense to everyone? Perfect. Likewise, at carbon 2, I have this tert-butyl group, and this tert-butyl group is axial pointing up. So this would be the two conformations for the following molecule. Does that make sense to everyone? Does this first example make sense? So make sure to number your carbons and make sure that you're drawing out your cyclohexane chair conformations with the consistent orientations. Okay, let's look at this second example. So I'm going to label my carbons. So in this case, I'm going to put this methyl at carbon 1 arbitrarily. You can also choose, if you want, you can number the chlorine at carbon 1 and then count clockwise around the ring. In this case, we'd have axial, equatorial, axial, equatorial, axial. Since both of these substituents have dashes instead of wedges, we use the opposite label. Then, now that we have our carbon labeled, we draw out our base cyclohexane chair conformation. We put the chlorine in the axial position, pointing up, because this chlorine at carbon 1 has a wedge. At carbon 6, the chlorine has a dash. So whoops. Sorry about that, I missed a label, so let me reset that. So we have alternating axial and equatorial assignments for wedge. Since they're dashed, we use the opposite assignment. At carbon 6, our chlorine has a dash, so the chlorine is pointing down. So this chlorine at carbon 6 is axial, pointing down. And at carbon 5, our methyl has a dash. So then our methyl would be equatorial, pointing down. Does that make sense to everyone? Does everyone understand how I use my carbon numbers in the dash wedge notation to assign my substituents? Number your carbons. You do not want to move substituents to adjacent carbons because that would actually change the stereochemistry, or you'd end up accidentally drawing a constitutional isomer. So now after a ring flip, so carbon 1 goes down, carbon 4 goes up. So at carbon 1, our chlorine is now equatorial, pointing up. So 1, 2, 3, 4, 5, 6. At carbon 6, our chlorine is now equatorial, pointing down. Since when we undergo a ring flip, our axial and equatorial substituents flip. At carbon 5, our methyl that was previously equatorial pointing down is now axial pointing down. Does everyone see how in a ring flip, carbon 1 is now at a different relative position? Does everyone see how critical it is to keep your carbon 1 label consistent? Does this example make sense to everyone? One way to check your work is just to make sure all of your wedge substituents are up and all of your dash substituents are down. So Based on that check, both of the conformations that we've drawn seem perfectly reasonable. Any questions on these examples? If not, let's keep going. And let's look at and begin our first discussion of conformational analysis. So in this case, we're looking at the conformations of monosubstituted cyclohexanes. So the cyclohexane ring rapidly flips between the chair conformations at room temperature. The two conformations are not equally stable. The equatorial conformation, equatorial conformer, is generally more stable, and for methylcyclohexane, it's more stable by about 7.6 kilojoules per mole. And of course, we know that the equilibrium constant is based on the difference and it's proportional to the difference in Gibbs energy of our two conformations. So remember this equation that you talked about in 102 that related the equilibrium constant to the Gibbs energy of our reaction, or the Gibbs energy comparing our reactants and products in an equilibrium? Same principle. The difference in energy between our reactants and products directly affects, or the difference in energy between our two conformations in this case, directly affects the amount of each conformation found at equilibrium. So what this means is, in general, the equatorial conformation is generally lower in energy, and as a result, it's more prevalent at equilibrium. So we can see this idea of the relationship between the equilibrium constant and the Gibbs energy difference between our two conformers in the following table. As we notice, the larger our energy difference, the greater the difference in the amount of each conformation at equilibrium, right? Does everyone see how the energy difference between our two conformations is directly tied to the amount of each conformation that we see? Does everyone see how if the energy difference gets larger between our axial and equatorial conformer, then the more of our lower energy conformation we expect to see at equilibrium? Does that idea make sense? Okay. So the equatorial conformer is more stable. And just like in the conformational analysis of acyclic systems, we can quantify the amount of steric and torsional strain found in each of our conformations. So we see in this case, for our axial conformer, we have a steric interaction between a methyl and a hydrogen. And we have two methyl hydrogen steric interactions. And this gives us about an energetic penalty of 7.6 kilojoules per mole of strain. Does this number look familiar to anyone? Does this number ring a bell? What's another word for like a methyl? So what's another? Where does that 7.6 look familiar? In other words, we have two interactions with a penalty of about 3.8 kilojoules per mole each. Another way to visualize this is I'd like you to think a little bit and treat each of these groups like they were a methyl group. Like treat each of these carbons as if they were a methyl group. What do we call this methyl-methyl interaction? More specifically, this methyl-methyl interaction that occurs when the methyl group and a hydrogen are in close proximity. What do we call this interaction? We saw this in our analysis of acyclic systems. What do we call an interaction when we have bulky substituents close together in space? What do we call that interaction? I'll give you a hint. This interaction is very, very similar to an interaction that you'd see if you have a methyl group and another methyl group on an adjacent carbon. Yep, this is a Gauche interaction. Exactly right. So these steric interactions that we observe are actually known as Gauche methyl interactions. And it's based on this idea that our substituents take up space and there's a steric interaction between the methyl group and the hydrogen attached to our adjacent carbons. That's where this 7.6 comes from. It's the exact same energetic penalty as two Gauche interactions. Does that make sense to everyone? Does everyone see that parallel? Let's unpack that. So 1,3-diaxial interactions are coined because they're interactions between our axial substituent and the adjacent other axial substituents at carbons 3 and 5. So it's interactions between our axial substituents that result in steric strain. This is why our equatorial conformer is lower in energy, because when we're in the equatorial position, we have no steric interactions. There's no 1,3-diaxial interactions when our substituent is equatorial. So to help us see that, to help us visualize how that works, let's make a quick little model. So I'm going to put together a model using a model kit. And let's take a look at that model. And let's try to analyze what's going on. And let's try to draw some parallels to our Gauche methyl interaction. So one moment, I'm just putting together the model for this structure. Okay. So, as we can clearly see, when our methyl group is axial, it can bump into our other axial substituents. So it's engaging in steric interactions with our axial substituents. If our methyl group is in the equatorial position, is our methyl group close in proximity to any of our substituents? Is our methyl group as close to any of our other substituents? Or is it relatively isolated in space? It's relatively isolated. So when the substituent's equatorial, we don't see any of these destabilizing steric interactions. Okay. Now, to tie back and to help us understand steric strain depends on our substituents, and it depends on the size of our substituents. So strain depends on the substituents. and we use Y values, or what are known as quote unquote A values, to assess the amount of steric strain associated with an axial substituent. So for example, a methyl group for a single methyl hydrogen diaxial interaction costs us about 3.8 kilojoules. Okay. An ethyl group, which is larger, has more steric bulk, we pay a greater penalty. Now, if we really start to look at exciting structures and we start to look at what happens if we have a T-Butyl group, and we start to have a T-Butyl group axial, what's the problem with a T-Butyl group? What's a big problem with a T-Butyl group? How bulky is a T-Butyl group? Let me just show you on the camera, because it really is hard to appreciate when you're just drawing the bond line structure. But if you look at a T-Butyl group, so if we have a T-Butyl group axial, does everyone see the monster T-Butyl group right here? Is this T-Butyl group just bumping into everything? So our ring is down here. On top is this giant T-Butyl group. Does everyone see why this T-Butyl group has such a large amount of steric strain? Because it takes up a huge amount of space. In general, the less space your substituent takes up, the lower its 1,3 diaxial penalty. And we can see this actually quite clearly if we compare a T-Butyl group and methyl group to something like a nitrile. Why does a nitrile have such a low A value? Why does a nitrile have such a low A value? Well, let's look. Let's look and see. If we put a nitrile, what do we notice about the nitrile? Does it take up a lot of space? Does this nitrile take up a lot of space? Looking at its geometry, it still has a fair number of atoms, but because it has a linear geometry, this nitrile doesn't exert a lot of steric strain. It's not really bumping into any of our other axial substituents because this nitrile is linear. So the geometry of our substituents directly affects the amount of steric strain those substituents exert. Does that make sense? Because the nitrile is linear, it doesn't have any hydrogens that can engage in substantial 1,3 diaxial interactions with our axial hydrogens. If we compare that to a methyl group, does everyone notice because our methyl group has a tetrahedral geometry, its hydrogens are spread out in space, and as a result, those hydrogens on our methyl group can engage in 1,3 diaxial interactions, and that results in an increased amount of steric strain. Does that make sense to everyone? Does everyone see how the methyl group takes up more space and is able to engage in more steric interactions than our nitrile? And that's strictly a function of shape. Shape, which in turn influences steric bulk. So you can use this table of Y values as well to also estimate Gauche butane and torsional interactions as well. So this allows you to qualitatively compare the steric bulk and the torsional strain associated with different substituents. Does that idea make sense? Remember how I talked about on Tuesday how you'll get the table of A values can be used to qualitatively compare the amount of steric and torsional strain of different substituents? Well, here's the table. And it really hammers home this idea that steric bulk and the size and geometry of your different substituents directly affects the amount of steric strain. And we can quantify it. Does that make sense? Any questions on this idea? Okay, so axial substituents, destabilizing, 1,3 diaxial interactions, steric interactions, destabilize our molecule. We know that, okay? So when we think about 1,3 diaxial interactions, 1,3 diaxial interactions are actually a form of Gauche butane interactions. So if we look at our chair conformations, what we can do is, if we look down both of our carbon-carbon bonds, we can draw out a Newman projection. So let's showcase how that works. So suppose we have our chair conformation that looks, let me put the methyl at carbon 1 just to be complete. Okay, so here we go. So suppose we have the following. Okay, so I put together a model of this methylcyclohexane chair conformation. And suppose we have the following chair conformation. Oh, I got it. I realized that the camera flips things around. One moment. Let me make sure it exactly matches the conformation that we have. And you're going to want a model kit for this example, because it's really helpful to visualize and look down certain bonds. Okay, so we have our chair conformation. Does everyone see our methyl group? Does everyone see our methyl group? And does everyone see how this matches the chair conformation on the left? Does everyone see that for now? Okay, so what we're gonna do is we're gonna look down, and I'm gonna turn our view in a way that we're looking down this carbon-carbon bond with our methyl in front, and we're looking down our other carbon-carbon bond on carbon 5. So does everyone see how we're now looking down a series of carbon-carbon bonds? How we went from our chair conformation, which looks like this, and now we're looking down our carbon-carbon bonds. Does everyone see that? Does that make sense, what we're doing? We're looking down this carbon-carbon bond with our methyl in front, just like a normal Newman projection. And as with a normal Newman projection, we can draw the relative orientation of our substituents. So in this case, carbon 1 is right here, right? Does everyone see carbon 1 right here with the methyl group in front? And as we notice, our methyl group is pointing up and our hydrogen is pointing down. Now, looking at this portion of our ring, is this portion of our ring right here in front pointing up or down? Is this pointing up or down? Just looking at this relative to our methyl group. Is this ring portion pointing up? It's pointing down, right? That's why it's drawn pointing down. Does that make sense? This is carbon 6. Okay, now we can draw all of the substituents on our front carbons. So we've drawn out our methyl and our hydrogen, and we've drawn out our 2 hydrogens. And then we can draw the substituents in the back. So does everyone see in the back, behind the methyl, we have two hydrogens. Does everyone see these two hydrogens in the back? And those hydrogens are drawn right here. Okay. Now, if you want to do a ring flip, so let's execute a ring flip. So after a ring flip, as you notice now, after a ring flip, we have our methyl now equatorial. Now, again, what we can do is we can look down our carbon-carbon bonds, and what we can do now is we can draw an alternative set of Newman projections, okay? We'll talk more about the mechanics of drawing these Newman projections in a moment. What I want you to focus on now is, does everyone see how we get these Newman projections? We're looking down our carbon-carbon bonds, we're drawing our front carbons and their substituents, and then drawing our back carbons. Does that make sense? Is everyone with me so far on that?
Yep.
Okay, so now what we're going to do is the relationship between these Newman projections and Gauche butane interactions is that if we look really carefully at when we have an axial cyclohexane, so when we have an axial cyclohexane, and we have our methyl group in the axial position. So we have our methyl group in the axial position. If we look down our carbon-carbon bonds, one thing that we notice immediately when we look down our carbon-carbon bond is that if we look down this bond, do we see that our methyl group, and we look at this CH2 group. So looking at the methyl group and this CH2 group from the perspective of our Newman projections. Does everyone see how this methyl group and CH2 group, it looks very similar to a methyl-methyl interaction? So to help you see that, if I disconnected this CH2 group, and we were just looking at this interaction, does everyone see how this methyl group and our methylene, this interaction almost exactly looks like a methyl-methyl Gauche interaction? Does everyone see that? Does everyone see how this methylene in our ring is functioning exactly like a methyl group for a Gauche methyl-methyl interaction? Perfect. So that's why the energetic penalty for a 1,3 diaxial interaction is very similar to that of a Gauche butane interaction. So the Gauche butane is less stable than the anti-butene by about 3.8 kilojoules per mole as a result of these steric interactions. So again, we can think about our methylene very similar to that of a methyl group in terms of Gauche interactions. So this 1,3 diaxial interaction can be thought of as like a methyl-methyl Gauche interaction. As a result, for each of our 1,3 diaxial interactions, we pay a penalty of 3.8 kilojoules per mole for a total penalty of 7.6 kilojoules per mole. Does everyone see the parallel between the Gauche butane interaction and the diaxial interactions? Does that make a little bit more sense to everyone? Perfect. So in general, just something to keep in mind, equatorial positions give the more stable conformer. Okay, so when we start to get to di-substituted cyclohexanes, in di-substituted cyclohexanes, the steric effects of both substituents must be taken into account. So we're going to start to look at multiple different diaxial interactions occurring at once. So let's look at 1,2-dimethylcyclohexane. There are two isomers, cis and trans. So for the cis isomer, which looks something like this, in this case, we have one of our substituents axial and the other substituent equatorial, both of them pointing up, right? Does everyone see how one substituent's axial, one's equatorial, both are pointing up? Now, as we can see in our first conformation, we have two methyl hydrogen 1,3 interactions. So we have 2 times 3.8 or 7.6 kilojoules of energetic penalty. Now, what's really important to consider here is that we have our diaxial interactions, but we also have a gauche interaction. Where is this gauche interaction coming from? Well, we can explain that. Does anyone have a guess? Where's that gauche interaction coming from? Does anyone have a guess for that? Well, this is where we need to pay special attention to our Newman projection model. Okay. Okay, so here's a model of cis dimethylcyclohexane. So here's a model of cis 1,2-dimethylcyclohexane, okay? So we have our methyl in the front and the methyl in the back, okay? Does everyone see that? So here's our first methyl in the front, and then our second methyl is in the back. It's a little hard to see. Does that make sense to everyone so far? Okay, now, where's this gauche interaction coming from? Well, if we look down with our eyes and we look down, and we look down this carbon-carbon bond. We're using our eyes and we're looking down this carbon-carbon bond. What we see is that we have a methyl group pointing up. We have the hydrogen and we have the rest of our ring. Allow me one moment to reset OneNote. It gets a little bit overloaded when I have this many drawings present. Give me one moment to reset OneNote. Give me one moment to reset OneNote, especially for these longer chapters. Once there are a lot of files up, sometimes OneNote gets a little bit overwhelmed. Okay, so I've reset OneNote. Can I just get some confirmation that everyone can see the screen right now?
Yeah, I see it.
Okay, perfect. Okay, so continuing on with our discussion. Okay, so we had our 1,2-cis-1,2-dimethyl cyclohexane. Now what we're doing is we're looking down our carbon-carbon bond and we're drawing what we see. So, does everyone see an immediate red flag when we look down this carbon-carbon bond? Does everyone see when we look down this carbon-carbon bond and we look at our two methyl groups? What do we notice about our two methyl groups? Are these methyl groups close or far away in 3D space? They're very close. So if we look down this carbon, we would have our methyl group and a hydrogen, and then we'd have our equatorial methyl group and a hydrogen. And as you can see, we have a Gauche interaction between our two adjacent methyl groups. Does everyone see where that Gauche interaction is coming from? Yes, and this interaction is present in both of our conformations. So after a ring flip, we bring our carbons, one carbon down, the other carbon up. And now, as we notice, we still have 1,3-diaxial interactions. So we have two 1,3-diaxial interactions, or two methyl hydrogen 1,3-diaxial interactions that costs us 7.8 kilojoules. And as we can see from this picture, it's pretty easy to see that if we look down this carbon-carbon bond, we also have a methyl-methyl Gauche interaction. Does that make sense? Does everyone see that Gauche interaction clearly in this picture here? So then, if we add up all of our energetic penalties, what we see is that in this case, both conformations have the same energy. So both conformations are equally preferred at equilibrium. Does that make sense to everyone? Okay, so let's keep going now. And let's look at the following example. So in this case, cis-1,2-dimethyl cyclohexane would be drawn from the following dash wedge depiction. So it's important that you correlate these chair conformations that we are drawing with dash wedge depictions. So again, here's our two conformations of 1,2-dimethyl cyclohexane. And both conformations are equally favored. They have the same amount of steric and torsional strain. Is everyone comfortable with this first example so far? So let's look at this next case. When we look at trans 1,2-dimethyl cyclohexane, both conformations are not equal in energy. So let's look. In one trans conformation, both methyl groups are equatorial with only a Gauche butane interaction between the methyls. In the ring flipped conformation, both methyl groups are axial with 4 1,3-diaxial interactions. Thus, trans 1,2-dimethyl cyclohexane, due to this large energy difference between the two chair conformations, will almost exclusively exist in the di-equatorial conformation. Because as we notice, when both of our substituents are equatorial, we only have a methyl-methyl Gauche interaction, and that's it. There are no 1,3 diaxial interactions. However, when we have our methyl groups when we undergo a ring flip and our methyl groups are now in the axial position, we see that we have 1, 2, 3, 4. We have 4 methyl hydrogen 1,3 diaxial interactions, which costs us 3.8 times 4, which gives us 15.2 kilojoules. Now, one interesting little curiosity that I'd like us to ask is, looking at this molecule and looking at the following picture, do we still have our methyl-methyl Gauche interaction? If we look at our methyl groups, do we see a Gauche interaction between our methyl groups in this conformation? No, exactly right. There are 4 methyl hydrogen diaxial interactions, but no methyl-methyl Gauche interaction. Why? They're separated by 180 degrees. It's this kind of detailed bookkeeping that you need to do in order to determine the lower energy conformation. Does that make sense? These subtle details can matter, so it's important that you take an accurate inventory of all of your steric and torsional interactions. Does that make sense? So we lost a Gauche interaction, and in exchange we gained 4 massively destabilizing diaxial interactions. So trans 1,2-dimethyl cyclohexane looks something like this, and we would translate it into the 2 chair conformations shown here. Does this example make sense to everyone? Does this conformational analysis example make sense? Okay, so let's keep going now. And let's draw both chair conformations of the following compound and identify the lowest energy conformation. Okay, so to start off, this ethyl group is up, this chlorine is down. So I'm going to write my initial labels, axial, equatorial, axial. And then since the chlorine is dashed instead of wedged, it has the opposite label of equatorial. In my first conformation, I'm going to draw my ethyl at carbon 1 pointing up, and then my chlorine at carbon 3 will be pointing down. Does this make sense so far? Does this make sense so far? Is everyone following so far? Okay, so now we're going to look at what happens after a ring flip. So we're going to bring carbon 4 up and carbon 1 down. Okay, and now looking at this, at carbon 1 now, my ethyl group is going to be equatorial. And at carbon 3, my chlorine will now be axial. I'm going to draw out the rest of my hydrogens because we need to see our hydrogens because we need to see our hydrogens to complete this analysis. There we go. So now that I've drawn out my hydrogens, let's do the same for our top structure. And now we're going to start analyzing our top structure. Okay, so in our top structure, let's take a tally. What interactions do we have? What interactions do we have in our top structure? What interactions and what are their energetic penalties? We don't have any adjacent substituents. So rather than calling them gauche, we'd call them diaxial interactions. And what kind of diaxial interactions do we have? What kind of diaxial interactions do we have? More specifically, this is not a methyl group, but an ethyl group. And this has a penalty of about 4.0 kilojoules. And we have 2 ethyl hydrogen 1,3 diaxial interactions. So we take 4 kilojoules times 2 for 8.0 kilojoules total. Do we have any other diaxial interactions? Oh, no, don't worry. I'm just trying to make sure that our interaction labels are as specific as possible because the ethyl hydrogen interaction has a slightly different energy because the ethyl group is a little more bulky. Are there any other interactions? Is the chlorine axial? Is the chlorine axial? It's equatorial. So would it experience any diaxial interactions? No. So the only interactions that we have are our 1,3 diaxial interactions involving our ethyl group. Okay, so we've tallied up all of the strain present in our first conformation. Let's look at our second conformation. So what interactions do we have in our second conformation? What interactions do we have in our second conformation? And try to be as specific as possible. We have 2 chlorine hydrogen 1,3 diaxial interactions. And would someone like to tell me, looking up our table from the A value table, what is the penalty for a chlorine hydrogen diaxial interaction? Well, let's look it up. Let's go to the table. I'm not expecting you to memorize these values, but I am expecting you to be able to make qualitative comparisons. Chlorine is clearly smaller than a methyl group, right? So we would expect it to have less diaxial strain. So the penalty is 1 kilojoule per mole. That makes sense. Chlorine is smaller than methyl. So we have 1.0 kilojoules times 2, and that gives us 2.0 kilojoules. Remember, chlorine is smaller than a methyl group, ergo it has less 1,3 diaxial strain. In general, you want to place the smallest substituents in the equatorial position. So which of these conformations is lower in energy? The conformation with the axial ethyl or the conformation with the axial chlorine? The second one, right? The axial chlorine is smaller, it has less steric strain. The second conformation has a lower total amount of steric and torsional strain. So this conformation would be the lower energy conformation by about 5 kilojoules. So we'd estimate that around 80% of the conformations at equilibrium would be this bottom structure. Does that make sense to everyone? Does this type of analysis make sense to everyone? So what I'd want us to do as our last activity for today's supplemental lecture, I'd like you to draw both chair conformations of the following compound and identify the lowest energy conformation. So this example is going to take us probably about 7 to 8 minutes. So I'd like us as our first step to draw both of our chair conformations for this compound. So let's try to get some drawn chair conformations for each of these compounds, so then we can analyze those chair conformations. So let's try to break out the annotate tool and let's try to draw out both chair conformations of the following compound. And then once we have the chair conformations drawn, we'll be able to analyze and calculate the total amount of steric and torsional strain. So don't be shy to contribute using the annotate feature or to send your proposed chair conformations as a photo in the chat. I'd like to have the class work on this example as a group, and I'll be happy to provide feedback as we start having chair conformations drawn out. So let's try to get a few structures drawn using the annotate feature. And we'll discuss this example in about another 5 to 6 minutes. And I'd really like to see a few structures drawn so that way I can provide feedback. And so we can begin discussing and analyzing those chair conformations. And if there are any questions that I can address, don't be shy to ask them verbally or in the chat. But I'd really like the class overall to, just like we did in previous examples, start drawing structures and in turn, analyzing those structures. This is exactly the kind of question that you'd see on an exam. Draw both conformations, identify the lowest and highest energy conformation. Any questions so far? Don't worry about trying to tackle the problem all at once. Start step by step. First, draw the conformations, and then we can start to assess their energy. So let me take a look at one of the student proposals. Yep, and the response that I received as a file in the chat looks reasonable. We have our first drawn chair conformation, and that looks good. Let me just rewrite it so that way it's visible in a bit of a larger font for everyone. But this chair conformation looks great. We have our ethyl up, our methyl up, and our chlorine. The only thing that I need you to double check is looking at our carbon numbers. The chlorine should be one carbon over. So this chlorine should be one carbon over and pointing down. Otherwise, this first chair conformation looks great. Remember that when you undergo a chair flip, the orientation of your cyclohexane ring will change. And let's try to get the substituents assigned in the second chair conformation after a ring flip. And for other students in the class, don't be shy to chime in and help your classmate out by helping them draw the second chair conformation or providing some input or feedback in the chat. So again, just to emphasize that after a ring flip, if you number your carbons, after a ring flip, the substituents need to be attached to the same carbon after a ring flip. Would anyone like to provide the other chair conformation for this compound? Or would you like to revise your submitted response? I'm really happy to see these responses as it helps me provide very directed feedback. Would anyone like to propose the other chair conformation after a ring flip? And would you be able to number your carbons? Is the chlorine in the right spot? Wait, sorry, looking 1 and 2, you have assigned the same carbon. Could you number your carbons once again? Okay, perfect. Yep. And where is the chlorine? What carbon is the chlorine on? Oh, it is on carbon 5. Okay, perfect. And the chlorine's pointing down. Yep, perfect. And after a ring flip, as the student has very correctly drawn, carbon 1 goes down, carbon 4 goes up. Our ethyl is now equatorial pointing up. Our methyl is now axial pointing up. And our chlorine is now equatorial. Our chlorine is now axial pointing down. So adding in our hydrogens to this process, we have both of our chair conformations drawn out. Let's add in our hydrogens and then let's calculate and identify the lowest energy conformation. So now that we have both of our conformations drawn, I'd like you to take a few more minutes and I'd like you to tell me the energetic penalty of each of our diaxial and torsional interactions for each of these two molecules. And then once we have accounted for all of our steric and torsional interactions, I'd like you to tell me for structure A and structure B for our two conformations, which conformation is lower in energy. So let's take about 3 to 4 more minutes and let's analyze which conformation is the lowest in energy. And let's try to get some responses in the chat for now that as a class we've drawn out the two different chair conformations. Which conformation is lower in energy and why? What does everyone think in terms of what's the lowest energy conformation? So we have some students suggesting structure B. Let's try to explain why. I'd like to see some responses in the chat for why do we think B is lower in energy, or why do we think A would be lower in energy? And we can calculate the total amount of strain in each of these structures, and we can use that data to support our argument. And we'll discuss this example in about another 1 to 2 minutes. Let's try to get a few more responses in the chat. Simply articulating your argument in these problems can help you both and can help me identify key points that I can emphasize further, and it helps you both practice and understand each of the steps necessary to solve these problems. Let's try to get a few more responses in the chat. Really don't be shy. And the more responses we have, the more diverse our class discussion in turn can be, as we'll have a range of different opinions and a range of different approaches to solving this problem. And we'll discuss in about another 1 to 2 minutes. Structure B, the methyl is axial, so you're on the right track. So we have a lot of arguments that structure B is lower in energy. So we have some arguments that structure B is lower in energy because we have a chlorine engaging in axial interactions rather than the methyl. So that is true, but let's look at each of these structures and let's look at all of the diaxial interactions step by step. And it's really important that you pay attention to all of your axial substituents. So in the analysis for structure A, only the ethyl is axial. So for our 1,3 diaxial interactions, what 1,3 diaxial interactions does structure A have? What 1,3 diaxial interactions do we have for structure A? Ethyl hydrogen. So we have 2 ethyl hydrogen interactions, which is 2 times 4.0, which is 8.0 kilojoules per mole. What other interactions do we have? So we have steric interactions. What about Gauche interactions? Do we have any Gauche interactions at play here? Is there a Gauche interaction in conformation A? Is there a Gauche interaction in conformation A? Do we have 2 substituents on adjacent carbons that are separated by a 60-degree dihedral angle? What do we think? Yes, so we have a methyl-ethyl Gauche interaction, which is approximately, again, 4.0 kilojoules. It's exactly the same as a 1,3 ethyl hydrogen interaction. So in total, we have 12.0 kilojoules of strain. Let's look at structure B. So in terms of diaxial interactions, so my methyl is axial and my chlorine is axial. So what 1,3 diaxial interactions do I have? What 1,3 diaxial interactions do I have? What 1,3 diaxial interactions do we have? Yep, so we have methyl hydrogen interactions and we have 2 of them. So we have 2 times 3.8, which gives us 7.6. And we also have a chlorine hydrogen interaction and we have 2 chlorine hydrogen 1,3 interactions, which is 2 times 1.0, which gives us 2.0. Additionally, we also have a methyl ethyl Gauche interaction once again, which costs us 4.0 kilojoules. Adding these together, this has a total penalty of 13.6 kilojoules. So the key thing I want you to keep in mind, your analysis comparing the ethyl and chlorine was reasonable. However, you need to make sure you account for all of the 1,3 diaxial interactions to determine the lower energy conformation. Does that make sense? Does that make sense? So then, which conformation is lower in energy, A or B? Wait, which one's lower? A, yep. So you need to consider all of your diaxial interactions when assigning your lowest energy conformation. It's quite close. So it'll likely be a bias of like 55% of this because the energy difference is only around 1 kilojoule. Oh wait, so then it'd be around 65, sorry. Does that make sense to everyone? Does this analysis make sense? This is exactly what you'd be expected to do on an exam and on the ACS. So this is a good example for us to end today's supplemental lecture on.